Hello class, I'm working out of your geometry book 6.1 to page 248 to get started. You do have definitions and a Venn diagram on 249 that are sets and subsets of quadrilaterals, as well as a few theorems in the pre-reading. So let's grab all of those for notes and then look at the diagrams as I go through this video as well to help you. All right, I'm starting on example 1, page 249, and we see two quadrilaterals that we're going to evaluate. The first one looks something like this. I'm working with a stylus, so I'm going to do just the best I can here. It is labeled A, B, C, D. Which of the defined subsets does this quadrilateral appear to belong? Well, these sides are parallel, and it is a rhombus. So we would say that. So we have a parallelogram, and rhombus. All right, the next figure looks like this. It's a trapezoid turned on its side. So we have WX, YZ in the flow, and we remember that we're going to evaluate this by looking at the sides. We have two congruent sides, this one and this one. It appears to be congruent. And then we have parallel sides. These are parallel sides to each other, WZ and XY. So we know it's a trapezoid shape. And if there are two congruent sides, think about our definition with triangles. We have an isosceles. Trapezoid. So these are specific names for the shape that you see. All right. We did talk about that the book diagram is always what it appears to look like, but may have completely different figures, angles, sides, and such. Here you're looking at what appears to be true, so consider that as well. And then label it as such. All right, if we have a figure such as K, O, M, J, and the sides are labeled such as 3y plus 2 for this side, 5y plus 2, 3x minus 1, and x plus 5. You're going to be asked to find the measure of each side of this kite, and you need to consider what is congruent to one another. We would consider JK to be equal to JM in this figure. Do look in the book. It's a little bit better than my drawing with a stylus. All right, so if that is true, we have JK is equal to JM. Then substitute in your expressions. JK is x plus 5 across the equal sign. JM is 3x minus 1. Again, you're asked to find the measure of each side of the kite. So we're solving for x and then substituting back in. Let's do that. If that is true, we're going to have 2x equals 6 with like terms, and x would equal 3 here. Okay, substituting back in, 3 plus 5 equals 3x, which is 3. minus 1. Let's see what we get here. We get 8 equals 9 minus 1, 8. So if that is true, we solved that JK is indeed equal to JM. All right. If we look at KL equals ML, the other two sides, and consider solving those, we're going to have KL is equal to ML, which means we would have 3y plus 2 is equal to 5y plus 2. Consider your distributive properties, solve that for your expression. Okay. And then utilize like terms to start solving algebraically. Solve for y. Y equals 2 here. We're going to substitute 2 back in for everything. So we have 3 times, put that in green, 2 plus 6 equals 5 times 2 plus 2. What do we get? Well, we'll have 6 plus 6 is 12 equals 5 times 2 plus 2 is 12. So KL is indeed equal to ML. So solve for your variable, substitute, and check that your sides are equal. You're finding the measure of each side of this kite. All right, we need to use slope and distance formulas to classify in our next shape. This is example 3 on page 250. Just to review, M equals slope. It's the rise over the run. So if your graph has a diagram on it and you can figure out rise over run, then you can figure out slope. Also, our distance formula, which we'll need shortly, is the root of parentheses x subscript 2 minus x subscript 1 to the second power plus y subscript 2 minus y subscript 1 all to the second power under that root symbol. Those kind of ran together. So let's look. State the most specific classification for quadrilateral RSTU. Alright, so from your Venn diagram, let's think a little bit. I have something going on like this here on the XY plane. Mine's, I didn't put in a grid on this, but here's what's kind of going on. In your diagram. So definitely be looking at your diagram in the book so you can figure out the slope here. In your subsets on the Venn diagram, a square is not a rectangle, but a rectangle is a type of square. When you're looking at sets and subsets of what a square falls as a quadrilateral. We're going to be considering that in this example. So a rectangle is a type of square, but a square is not a rectangle. If that is all true in your subsets, then we can look at our slopes. Look carefully on your diagram, example 3, 250, and find that the slope of M subset ST would be equal to a negative 2/3. Find your negative slope because visually that line has a negative slope on the grid. That's also equal to the slope of line RU. Alright, look carefully at the slope of RS. Consider it. It's a positive rise over run of 3/2, and that's also equal to the slope of UT. Find those. Consider rise over run. Use the visual on the graph to find your slope. We've done that in class along the way. Alright. Notice we have a negative reciprocal from one slope to the other. If we have a negative reciprocal, then figure R, STU is a rectangle. Opposite sides are parallel and the consecutive sides are perpendicular. So this perpendicular situation with our slope throws a negative reciprocal, if you remember that. Alright, using the distance formula, continue to consider your distances from the diagram in the book on 250. And we are going to pop that in. We're going to say, alright, side RS is equal to the root of x subscript 2 minus x subscript 1 squared plus y subscript 2 minus y subscript 1 all squared. So RS would be this when we pop in those values, 2 squared plus 3 squared. Where do we get those? Find your points, your plotted points x and y, to determine those. For line RS, okay, that all equals the root of 13, which is also going to be equal to line ST, which is also going to be equal to line TU, which is also going to be equal to line UR. If those are all equal, then we have the value and the distance for a square. Okay, so we solved with slope and distance formula to find that the classification of this quadrilateral can be a rectangle and a square. With the perpendicular situation in the slope through a rectangle, with the distance of the sides through a square. Remember, everything that we see in the book is an appearance, and so we work algebraically and with formulas to prove the distances. What you see may not be what you get, so jump that gap on deciding whether that's a rectangle or a square. Alright, we do have a proof on page 250. Consider your definitions for convex and concave. If you need to look those up and remember what that is all about, you're going to be using those ideas here in this proof. You're proving the sum of the interior angle measures are 360. That is twice the amount of the interior measures of a triangle at 180. 180 plus 180 is 360, so the quadrilateral is twice that amount. So look over that proof. A regular convex ingon has incongruent angles. So you're talking about some shape. And there's actually a formula for the measure. You have n minus 2 all times 180 degrees all over n for that formula. You might want to grab this for notes and or an index card. So if you're asked about the gazebo in example 4 on page 251, it's a regular octagon. An octagon has 8 sides. So to find the sum of the measure of the interior angles, you're going to have 8 sides minus 2 in the formula we just talked about times 180 degrees. That equals 1080 degrees. Now to find the measure of each interior angle, we're going to take that 1080 degrees divided by 8, and it's going to give you 135 degrees for each angle. And we consider 8 congruent angles for an octagon that each measure 135 degrees when we pop it into the formula. Okay, another example. If you have exterior angles that look kind of like this, again, I'm going to do the best I can to draw it with the stylus based on what's going on. Okay, remember a line is 180 degrees, and so when you're given these exterior angles like this, you're going to be asked for the sum of the measures of the interior angles. Alright, so on this line right here, 65, we have an acute angle. That means on the other side, you're going to have an obtuse angle, 180 minus that 65 equals what? Okay, so this angle is 115 degrees here on the other side. Calculate all 4 of them. So you're going to have, alright, here. This angle is 75 degrees, so on the other side, thinking of our linear pairs, we've got 180 minus 75. So this angle is 105. Kind of fat inside. Let me rewrite those in pen, guys. So 115 degrees. Okay, and so 105 degrees here. Alright, if we have this going on and you want to color changes when I change it. Okay, this one. This linear pair, you have 113 on this side. So we have 180 minus 113. So that's going to be 67 degrees on this angle. And we're going to have this one that we need to figure right here. So 180 minus 107 for those linear pairs. So this angle is 73 degrees. Alright, got through that. Now, if we need to check our interior quadrilateral angles, we know the measure needs to equal 360 degrees, so we can just check it real quick. All right, 115 plus 105 plus 67 plus 73. Add all those together, and we're going to get 360 degrees when we add all those together. So check on the measure of those interior angles. All right, I hope this helps. Consider your theorems, consider your definitions, consider your visual, consider your linear pair information that you know. You will need slope from the plane, rise over run. You will need the distance formula to prove that sides are the same, and then prove the set or subset of what you are looking at visually in your book. So if you need to just glance over and reread the pre-reading that would be suggested as a whole to work your assignment. Your formulas are available, and your information on labeling the quadrilaterals specifically are available in the pre-reading, so look back, get your fingers walking to help you out. I hope this helps, and I'll see you soon.